Hi everybody, welcome back to Viral Integrals. So today we're going to be evaluating the integral from 0 to 1 of natural log x over x minus 1. And a logarithm over x minus 1 looks like an endpoint trap, but it's really the Basel sum in disguise. The clue is that the denominator can create a geometric series while a parameter derivative in the numerator there can create the logarithm, and you'll see what I mean here in a second. Before doing any algebra, let's just check that the integral is reasonable. So between 0 and 1, both natural log x and x minus 1 are negative, and near 1, their ratio approaches 1 instead of blowing up, so we're good. So in a previous video, we derived the Basel result, which gives the value of the reciprocal square series. So the plan is not to reprove the Basel result here. The plan is to turn this integral into that exact series. So first, we're going to introduce a parameter by putting a power of x in the numerator. So this choice is deliberate. Differentiating x to the a creates the natural log x that we need, and the minus 1 keeps the quotient well behaved near x is equal to 1. And because the limits are fixed, we can use the Leibniz Rule for differentiation under the integral sign to pass a derivative inside the integral. Now the derivative acts only on x to the a minus 1, so the logarithm appears exactly where we want it. So this is our derivative f prime of a. F prime of a has x to the a times natural log x over x minus 1. This is the payoff for adding the parameter. The original logarithm is now part of a controlled family of integrals. Now we set a equal to 0. The factor x to the 0 becomes 1, so f prime at 0 is exactly the integral we started with. That means we can compute the target by computing f prime of 0 another way. To compute f of a, rewrite the quotient with denominator 1 minus x. Flipping both signs changes nothing, and now the denominator matches the geometric series 1 over 1 minus x. Now we substitute the geometric series into f of a. This changes the parameter integral into an infinite sum of much simpler pieces, each multiplied by 1 minus x to the a. Now just distribute the x to the n across the numerator. Each term becomes x to the n minus x to the n plus a, which is useful because both pieces are ordinary power integrals from 0 to 1. Now move the integral through the sum and integrate term by term. The reason this helps is that every term has the same simple shape, so the whole problem is reduced to evaluating powers of x. The two power integrals give reciprocal denominators. Integrating x to the n gives 1 over n plus 1, and integrating x to the n plus a gives 1 over n plus a plus 1. Now put those power integral values back into the sum for f of a. Notice that the parameter only appears in the second denominator, which makes the next derivative very clean. Differentiate the series for f of a. The first fraction is constant with respect to a, and the derivative of negative 1 over n plus a plus 1 becomes positive 1 over that denominator squared. Now set a equal to 0 in the series derivative. The denominator becomes n plus 1 squared, and earlier we already showed that f prime of 0 is the original integral. Reindex the sum so it uses the standard Basel notation. If m equals n plus 1, then n starting at 0 becomes m starting at 1, and the sum is exactly the reciprocal square series. Now use the Basel result from the previous video. Since the integral equals the reciprocal square series, and that series equals pi squared over 6, the integral has that same value. And a quick size check supports the answer. The first few reciprocal square terms are already positive and below 1.6449, so the final value is positive and in the expected range. So the integral from 0 to 1 of natural log x over x minus 1 is pi squared over 6. The denominator created the geometric series, and differentiating under the integral sign created the logarithm.